So in this video, we're going to look at the reaction of taking an acid chloride and converting it into an ester. So an acid chloride is this general structure. So you have, this is known as the acyl groups. This is also known as an acyl chloride. And then you have a chlorine. So this is a carboxylic acid derivative. So carboxylic acid derivatives all have the same oxidation state as a carboxylic acid. So you'll have a carbon basically with 3 bonds to something that is more electronegative than carbon. And so here is the acid chloride. And of your carboxylic acid derivatives, this is the most reactive for a nucleophilic acyl substitution reaction. So substitution means you're going to be substituting that group that is attached to the carbonyl carbon. And so the chloride is a really good leaving group, as you may remember from back when we talked about substitution and elimination reactions. So it's a good leaving group because it's a really weak base. So what we're going to do in all of our nucleophilic acyl substitution reactions, we're going to replace a leaving group with a nucleophile. So if we are looking to make an ester, let's draw the structure of an ester. So here's that same acyl group, and what you've replaced the chloride with, if you're making an ester, is another oxygen and another carbon-based group. And so this is the structure of an ester. And so if you look at the ester and you look at what has been added, what type of ester it is, that allows you to see what nucleophile is needed to make it. So this tells you what nucleophile is needed. Because this is a nucleophilic acyl substitution. So when you're making an ester, your possible nucleophiles need to look like what you're adding. So you could possibly add that as the alkoxide, or you could add that as the neutral alcohol. So which alkoxide or which alcohol you choose completely depends on what you're trying to make. If you're trying to make a methyl ester, you would need methoxide or methanol. If you're trying to make an ethyl ester, it would be ethoxide or ethanol. So let's look at an example of this. So let's say, for example, that we want to make methyl benzoate. And that's all we know. We want to make methyl benzoate using this sort of reaction. So we're going to want to take a look at the structure of methyl benzoate. So that means it is the methyl ester of benzoic acid. Right? So if this was OH, it would be benzoic acid. So if it's methyl benzoate, we have OCH3. So if we look at what we're transforming here, right, this tells us that this part of the molecule is coming from the nucleophile. And the remaining part of the molecule would be coming from your electrophile, which is your acid chloride. Okay, so looking at our nucleophile options, right, if it's a methyl ester we want, then we could use either methoxide or we could use the neutral alcohol methanol. So those are our 2 options, okay? And the acid chloride is going to have to contain this ring. So let's take a look at one example, and we'll use the methoxide first of all. So the acid chloride that we're going to want is going to have this structure, and then it's going to have the chloride. Right? And if we take and we react this with methoxides, we're going to look at the mechanism. This is going to be the general pattern for a mechanism for a nucleophilic acyl substitution. So we've got a good nucleophile and you've got an electrophilic carbon. So we are going to attack that electrophilic carbon, And it might be tempting to just break this bond to the chloride, kind of like an SN2 reaction, but that's not what happens when you have a carbonyl. We're going to instead break the pi bond. And so what this is going to give us is an intermediate where we have 4 things attached to that carbon, meaning it will be a tetrahedral carbon. So let's go ahead and draw that. Right, so now we have extra electrons on that top oxygen, so it has a negative charge. We still have the bond to the chlorine, and we have the new bond that was formed to that methoxide. So this sort of intermediate in this reaction, because it's tetrahedral, is known as the tetrahedral intermediate. Right, and so if this is a really stable intermediate, if you didn't have a leaving group attached to that carbon, this is where your reaction would stop until you added in a proton source and you would get an alcohol. But with an acid chloride, you've got a really, really good leaving group. So what's going to happen is the electrons from the oxygen are going to come back down to reform the pi bond and kick off that really good leaving group. And this is how we eventually do the replacement. So your nucleophile has replaced the chloride on that acyl carbon, hence the name nucleophilic acyl substitution. So then we will end up with our ester product. Okay, and we are technically also forming some chloride ion, which will just be in solution and probably removed in the reaction workup. Okay, so this is how the reaction would proceed if you are using your negatively charged nucleophile. And with something as reactive as an acid chloride, we can even get away with using the weaker alcohol nucleophile. The only thing that we're going to do if we're using the alcohol, you're also going to end up with a hydrogen that's acidic, right? After it attacks, you're going to have a hydrogen still attached. So you're going to be eventually building up HCl in the solution. So we often add a base to keep the reaction kind of buffered, kind of neutral. So we often add in pyridine when we use a neutral nucleophile. And so this is the structure of pyridine. And so the pyridine is just there to react with the HCl that will be generated in the reaction, right? HCl, hydrochloric acid, is a strong acid. We don't want that building up in the solution, so we often add in a base that will react with it as it's being formed. So this was our mechanism we just ran through with a anionic nucleophile. So we're going to take a quick look at the mechanism with a neutral nucleophile. So it's pretty much exactly the same. The only thing is we're going to have an additional step to remove this proton because it wasn't removed before the reaction started. So let's take a look at that. So we would start with the same acid chloride. So there's our acid chloride. All right, so we'll say this is our reaction with a neutral nucleophile. Okay, so the nucleophile instead of methoxide is going to be the methanol. So we will draw that methanol. So same as before, it's going to attack the carbonyl carbon, pushing those electrons up onto the oxygen, giving you a tetrahedral intermediate. So you have your tetrahedral intermediate. And just like before, now this tetrahedral intermediate will collapse and push off that really good chloride leaving group. So you're going to end up with a structure that almost looks like the ester that you're wanting. It's just that this hydrogen, we haven't removed it yet, so it will still be attached. And so here's where you need a base, so something like the pyridine, to remove that hydrogen. So the pyridine can remove that hydrogen, giving you the ester. So you've still formed the exact same ester as a product. And what you're going to have as a byproduct, instead of just the chloride, you're also going to have a counterion to that. So you're also going to have pyridinium chloride, right? So we've added a proton to that nitrogen, and then the counterion chloride would sit nearby. But if you're asked for a major organic product for the reaction, which is what we tend to focus on, we would only need to focus on the ester product. So if you're asked for the major organic product, this is what we're talking about. Okay, so what we're seeing overall is that we can take an acid chloride, we can make an ester, we can use either the stronger alkoxide nucleophile or the weaker neutral alcohol. Either way, we would select the structures that we need by examining what we have. So the portion that has the carbonyl is going to come from your acid chloride, and your OR prime is going to come from your nucleophile.